Hello, everyone. Good afternoon. Can you hear me? Great, thank you. Okay, so we have our first exam on next Wednesday, and my plan is I'm going to begin today by going over quiz 2, which will serve as the review for the material on control theory, and then on Monday I'll review the interfacing material. I'll go through it fast, but to give everyone an opportunity to ask any questions about anything that you may still be unclear on with that. I'm also going to begin the next lecture on real-time scheduling today, and I'll continue that on Monday. I don't know if I'll get all the way through that, so I haven't decided yet whether I'll cover that on the exam or just wait till next exam. We'll see how we do today and Monday. Okay, so let's share. Share PowerPoint. And yeah, there it is. Okay, so quiz 3 begins by asking which of the following of these four equations is an LTI, a linear time invariant system. The rules for these is that you can't multiply or divide two signals in an LTI. So the first option here, you've got the derivative of g divided by g. Some of the slide is cropped on the left. Okay, sorry about that. Thank you. Let me try that again. Does that look better? Is that better? Hopefully. It's the same. Okay. Okay, let me reshare. Hold on one second. Share PowerPoint. Okay, is that better? If not, I'll just I won't maximize it, or I won't do a slideshow. Same. Okay. All right. Well, that's all right. I just won't do a slideshow then. I don't know why it's cropped. Okay. Okay. So so the first option, we have the derivative of g and then divided by 2g. So that's not an LTI because you're dividing g, signal g, or g of t. Yeah, the second option, you're multiplying the derivative of g times g again, so that's not an LTI because you're multiplying two signals together. The third option is derivative of g plus 2 times g, and that one's good. That's an LTI. And then the fourth one, you're squaring g, and so that one's not an LTI, right? So the answer here is the third option because it is a linear function of signals. So next question is, which of the following is the S-domain form of f of t equals dgt dt? So in this case, you're doing the derivative of g. So first of all, notice that when we do the S-domain transform, the Laplace transform, we capitalize f and g, and then instead of being functions of time, they're functions of s. And so when you do the derivative of g of t, that is transformed as just s times g of s. And so that's the correct answer, is the second one there. If it had been an integral gt, then the answer would have been G of S over S. So the answer there is the second one, SGS. And which of the following is a method for determining if a system is stable? Check if the order of the denominator polynomial of the transfer function is 2 or less. That's not correct. Check if the numerator of the transfer function is non-zero. That's not correct. Check if any poles of the transfer function lie in the left-hand plane. That one is close. But if in order for the system to be stable, all of the poles have to lie in the left-hand plane, not any poles, right? So that one that's tricky, because it's very close to being correct, but it's not actually correct. The correct answer is check if the impulse response of the transfer function is bounded, meaning that the function doesn't go to infinity as you increase the t. So yeah, so that third option is very close, but it's not exactly right. If I had said check if all the poles of the transfer function lie in the left-hand plane, then it would have been correct. But I guess the difference there is the word any versus all. Okay, so this one, okay, this looks like a lot of math because this is supposed to be animated, but because I can't do slide, for some reason when I go to slideshow mode, it's cropping the left side. But I'll just, if you just follow my mouse pointer, I'll show you how the order in which I did these. So which of the following are valid eigenfunctions of the transfer function 1 over s squared minus s minus 56? So I took the denominator and I factored it to s minus 8 times s plus 7. And then I wanted to decompose this into a sum of two components that are of the form, a over s minus a, because this is the form that you can do an inverse Laplace transform with to get the eigenfunction. The eigenfunction is basically just an exponential. So I rewrote this as a over s minus 8. So basically, you take the two terms in the denominator, you break them apart, and decompose or convert that to a over s minus 8 plus b over s plus 7. And then you do this trick where you convert these denominators back into the original denominator by taking s minus 7 and multiply it by a, and then change its denominator to s minus 8 times s plus 7. And then the second term would be b times s minus 8 over s minus 8 times s plus 7. So basically the idea is that you break this apart, you break apart this term into a sum, and then you make the denominators what they originally were, and then we can essentially multiply both sides of the equation by that denominator s minus 8 times s plus 7, and then we'll have 1 equals a times s plus 7 plus b times s minus 8. This is we're solving for a and b, so we have two unknowns in one equation. So this is an underdetermined system, but we use this trick where we'll set s to be minus 7, which will knock out the term a times s plus 7, because we'll have minus 7 plus 7 is 0, so that'll be a times 0, and we're left with 1 equals s minus 8. Well, we're setting s to minus 7, so that's going to give us 1 equals b times negative 15, and so b is negative 1/15, and then likewise to solve for a, we'll set s to be 8. To solve for for a, we'll set sorry, I'm over here. Sorry, we'll set S to be 8, which will knock out the B side, right? So we'll set, because we have B times S minus 8. If S is 8, we have 8 minus 8 is 0. 0 times B eliminates that side, and we have a 1 equals A times S, A times 15, actually, 8 plus 7. So A will then be 1/15. So that will give us if we go back to the original, this form, A is 1/15, and that'll be divided by S minus 8 plus negative 1/15 over S plus 7. So this is the decomposed form of the original expression. And then now that it's in this form, you're doing just a table lookup, essentially, to then convert each of these sides to this eigenfunction form, which would be 1/15 e to the power of 8t, because the conversion is 1 over s minus a is e to the at, right? So the 8 is the a, and so we substitute that in, and then the 1/15 just becomes a coefficient, a linear coefficient. And then likewise on this side, it's negative 1/15 times e to the negative 7t, because it was s plus 7. So this, the a is, because the template for this is 1 over s minus a in this case would be negative 7. So we bring that up to the exponent here. So these are the eigenfunctions from the original S domain expression. This is basically an inverse Laplace transform, is what we've done here. Okay, what is the next question? Is what is the transfer function resulting from feeding the function 1 over s plus 1 into function s over s squared? Now this is probably a little bit sloppy terminology. I should have said feeding the output of transfer function 1 over s plus 1 into another transfer function, which is s over s squared. But it's an easy question. You just multiply these two transfer functions together. So you end up with s divided by s plus 1 times s squared. And then you can reduce that to 1 over s squared plus s by dividing the numerator and denominator by s. Now, you don't necessarily have to do that. The reason I did it is because this is generally the form that you'll find transfer functions are usually like in a usually shown as a ratio of polynomials. That's not always the case. It's just kind of what you see. But if I gave you this form as the answer, that would be still it's technically true. I mean, all three of these versions are correct. Actually, even the first one too. Actually, they're all correct. They're all equivalent. Okay, this next one is you are designing a cyber-physical system to counteract the movement of a regular pendulum. I say regular as opposed to an inverted pendulum, which is a kind of a benchmark type of control problem. That was what I mentioned at the beginning of the semester. That's kind of what what a hoverboard is an inverted pendulum. This is just a hanging pendulum, regular pendulum. Now, how would you counteract? Like, how would you actually? What would a system look like that does that? I guess it would be like a pendulum, and then you'd have some sort of actuator at the pivot point at the top that would try to move it back and forth, but it's not important. that detail isn't really important. The point is that we're targeting a pendulum as the system we want to control, because you can describe it with an LTI. So for this, you need to model the physical system for your plant, which consists of a hanging pendulum whose angle is theta of t, and the system input is force f of t. The time domain equation for the system is f of t equals d squared theta t dt squared. So the second derivative of theta t equals minus b over m times the derivative of theta t minus g over l times theta t. That looks kind of complicated, but that's actually the pendulum equation. That also includes B, which is the friction. So when you look up pendulum equations, sometimes you'll see them without the friction component. So those are the ones that are sort of like, they have no friction. So once they get going, they just kind of go forever, like a perpetual motion machine. But with the friction in there, it'll sort of slow down. So in this equation, M is the mass, B is the friction, L is the length of the pendulum, and G is the is just gravity, 9.8 meters per second squared, and then F of t is the force being applied. So we're adding F, and theta of t is the angular position of the pendulum. So you have to be careful here. Obviously the force being applied here is an angular force. But again, that's not really that important. What is the S domain transfer function? So the idea is just to convert the time domain function to S domain. So to do the Laplace transform. So F of t becomes capital F of S. The second derivative is S squared. Second derivative of theta t is S squared theta S. And then on the other side of the equation, we have negative b over m multiplied by the first derivative of theta. So the ordering here is a little weird, but it's still good. It's minus b over m times s theta s. And then you have a last term is negative g over L times theta t, just becomes g over L times theta s. So that wasn't too hard, but it gets a little trickier because we need to get it into a form of a transfer function, which means that we need to get theta s, which is the output, to be a sort of a function of f of s, which is the input. And so that requires us to rearrange these terms. So on one side of the equation, we have theta s divided by f of s, and on the other side, we have basically just a ratio of polynomials of s. So to do that, you have to move the theta s to one side and all of the f of s's to the other side, and then you divide out the f of s, and then divide it by the both sides of the equation. So the first step here was to get actually I got the theta s, so this is s squared theta s plus b over m times s theta s plus g over L times theta s. So I got all the theta s terms on the left in this case, and then that is the only thing left on the right is negative f of s. And then I divided out the theta s. And then now the next part's a little tricky because I got to divide both sides here by f of s, and then divide both sides by this term, the polynomial. Okay, so once I did that, I ended up with negative 1 over s squared plus b over m times s plus g over L. So it was ends up being a proper polynomial. Now it is possible that you could get one of these with an integral in it, in which case you would end up with some negative powers of s. And if that happens, then you should fix it up so both polynomials in the right-hand side, in both the numerator and the denominator, don't have any negative powers of s. And you can correct for that just by multiplying numerator denominator by s over s, or s squared over s squared. Again, though, that's just to get it into a certain form that you expect. It's it's not necessary. The reason I mention this is because you might be saying, well, who cares if it's in what form it's in? If you open up Simulink in MATLAB and you drop down a transfer function, It asks you for, the only thing you give it are the coefficients to the polynomial, and it's assumed that the polynomial is in the the standard form. So that's the only reason I mentioned this. It's really kind of it's what the software expects. Okay. Next question is, what is the S-domain transfer function of a PID controller with the proportional term being 2, the derivative term being 1, and the integral term being 4? So the easiest way to do this is to just basically just put down the proportional term and by itself, and then the derivative term would be a coefficient of s, and the integral term would be a coefficient of s to the minus first power. And then, like I mentioned, in order now, this answer would be fine the way it is, but like I was saying earlier, you can multiply this by s over s, and you can get it into a proper ratio of polynomial form. Now, this question actually had a bug in it where the answer given didn't have the denominator s, and I fixed that, and I gave everyone credit for it. So you shouldn't have lost any credit for this if you didn't give the right answer, because the right answer wasn't on there until recently, and I apologize for that. But yeah, it should be s squared plus 2s plus 4 over s. But of course, if I gave you this question on the exam and I had the first one listed, 2 plus s plus 4 times s to the negative first power, that would also be correct as well. Okay, and this one is, what is the Tustin? Next question is, what is the Tustin transform of the transfer function f of s over y of s equals 1 over s squared plus 1 with t equals 1? Now, the Tustin transform, I went kind of fast in the lecture for this because I wanted to finish up this material so I could keep on schedule. So I'll just review this a little bit. So the Tustin transform is a way to get an S-domain transfer function into a Z-domain transfer function. And so why would we want that? Because S-domain transfer functions are continuous functions, and it is impossible to implement a continuous function on a computer because computers are discrete. Z-domain transfer functions are the discrete form of the S-domain. But the confusing part of that is that it's not like you can just take S and make it Z. It doesn't work that way. In fact, even the Tustin transform is an approximation. It uses the trapezoidal method to approximate a continuous function with a discrete function. And there's actually, in MATLAB, I think MATLAB has 6. There's like 6 different ways you can convert from S-domain to Z-domain, and Tustin is just one of the 6. There's one called zero-order hold, and I forget the other ones. The Tustin transform, by the way, is also sometimes called the bilinear method. In order to keep this material brief, I just covered the Tustin transform, but the Tustin transform is from my understanding, is kind of the most common way to do this, to do S-domain to Z-domain. Yeah. So yeah, Charles mentions that there's libraries that will let you make a function arbitrarily precise. Yeah, but I mean, still, technically for continuous, you need infinite precision. You'll never get that. But yeah, you can. And also, I should mention too, and I think I mentioned this in the lecture. Obviously, you've got software that can simulate a continuous system. I mean, you guys have used them. MATLAB can simulate S-domain transfer functions, and you can simulate things like in SPICE, for instance, as you hopefully did in your electrical engineering classes. In fact, a lot of scientific applications simulate continuous systems. So I'm not trying to say that it's impossible, But generally speaking, the way that you generally handle that is you just make the time step much smaller than the dynamics of the system that you're simulating, right? That's the way MATLAB does it. But the problem is that simulations aren't usually real time, and so when you want to do real-time simulation, you're constantly concerned about how small can you make the time step and still be able to maintain real-time performance of the system that's doing simulation. And so if you do this like arbitrarily, like in an ad hoc way, and your system is not, the time step that you're running at in reality is close enough to the dynamics of the system, then you'll end up with you'll end up with, the system won't be as accurate as it would have been if you had just done the Tustin transform and ran it as a discrete system, if that makes any sense. So there's actually a video online where a guy actually compared, he just took the S domain and he just did kind of a, an ad hoc, implementation of that in software, and then he did a state space version, but the Tustin version was actually the most accurate. So anyway, the point is that, yeah, we want to, the best way to do this is to take the S domain and discretize it into a Z domain to get the most accurate. It's still going to be, it's still going to look like, it's discretized. You're still not going to have smooth curves. You'll still see the zero order hold where you change the output and then the next time step is, and you change it again, and you have that little step up function. But this will get you close to the actual curve of the continuous function. Okay, so to do the Tustin transform, you replace S with 2 over t times z minus 1 divided by z plus 1, and then you kind of reevaluate and get it back into the form of ratio of polynomials. And like I said, this is actually doing a trapezoidal integration is what's really happening. I didn't derive this and explain why this is why you do it. I'm just giving you kind of how to do it. And if you're interested, you can, if you look online, there's a lot of derivations of this. But basically, it's real simple. You just take the S and put it in. In this case, t is 1. I'll assume t is 1 second, 1 second sample period. So that way t is basically goes away in the equation, and so you'll take the S and it'll be squared. So we have 2 over 2 times z minus 1 divided by z plus 1. That'll be squared, and so it's just a bunch of algebra at this point. The z minus 1, the 2 becomes 4. The z minus 1 becomes z squared minus 2z plus 1. The z plus 1 is z squared plus 2z plus 1. And then that plus 1 hangs off the end there. Now, I actually screwed this up when I was working this out originally, because I forgot that it's important at this point to take the 4 and multiply that through the numerator, which I do here. And then I can take that 1 and just make it z squared plus 2z plus 1 divided by z squared plus 2z plus 1, which is obviously equivalent to 1, but it gives us a common denominator. And then you can then add these two numerators together, which gives you 5z squared minus 6z plus 5. And then you can take its denominator and bring that up to the numerator, and you end up with z squared plus 2z plus 1 divided by 5z squared minus 6z plus 5. So just be careful when you work these out. I'm famous for making a arithmetic mistake when I do these. So just be careful. Don't be like me. So that's the answer. Okay, so what is the closed, next question, what is the closed loop transfer function for the system below? This one is really easy. You just have to remember that the transfer function, which is relative to R, which is the set point, the reference point, is the open loop transfer function divided by 1 plus the open loop transfer function. In this case, the open loop transfer function is actually comprised of 3 components, 3 systems, 3 LTI systems, 3 transfer functions that are connected in series. And so, you just multiply those together, so you get FGH. Now, you might notice that this is shorthand, by the way. This is a shorthand form because notice that there's no S in here in parentheses. And also notice that the transfer functions are being represented as a single value as compared to a ratio, right? Transfer functions are ratio. So like, for example, this is actually G over F. This is G of S over F of S, this guy. But I'm dropping that and using this shorthand notation. So I'm dropping the S and I'm dropping the denominators. So it's just F times G times H, but it's implied that this is actually G of S over G of S over F of S, this guy. And this guy would be, H of S divided by G of S, right? But this is, again, this is a shorthand. This is pretty common to see it done like this. So the answer is just FGH, which is the open loop transfer function divided by 1 plus FGH. So that gives you the closed loop. Now, this open loop function might actually be a nested closed loop system in and of itself. You can nest these things, much like you can, like think of it like a circuit diagram or, any kind of block diagram. These can be hierarchical. So this is a real simple one, but you can imagine, like in practice, you can have a fairly complex design here. Oh, in the S domain, yeah. So this would be F of S divided by the error of S, assuming this, we'll label this line the error term, which is the difference between the output and the set point, right? Or if you look at the lecture slides, I actually have it written as, it's F of S relative to H of S or R of S minus H of S to implement this addition or differencing block. But if we call this line, let's see, let me do that now, actually. If we call this E of S, here, if this is E of S, then this guy would be F of S divided by E of S, right? That's the that's the actual transfer function, but this is just a shorthand, shorthand way of showing it. And so this open loop is, is just the open loop divided by, or the closed loop is the open loop divided by 1 plus the open loop function. And of course, the transfer functions are just multiplied. When they're connected in series like this, you just multiply them. Okay, what is the discrete time domain implementation of the transfer function f of z divided by g of z equals 2z plus 3 divided by z squared plus 3z plus 2? So this one is I like this one. I like these questions because this is actually now bringing it back to software, essentially. So we're doing the inverse. This is the inverse z transform now. So we did the inverse Laplace transform, and we got eigenfunctions. Which the eigenfunctions ends up giving us the impulse response, right? But it doesn't help us much in terms of actually understanding the behavior of the integrals and the derivatives. With the z transform, it's a little bit nicer because we can do this inverse z transform, and we can actually then get an expression in the time domain which is in the discrete time domain, which actually maps directly to software. Now you might have been a little confused when I mentioned that last time because I didn't actually show you how you would do it in software. But the idea is that you would write a loop in software that would basically keep track of the last several samples. And when I say in the samples, would include both the input and the output samples. So f is the output and g is the input, but we end up with with code in this case when we convert this to code or convert it even into this time domain representation of the discrete transfer function. We end up with a function that calculates the current output, which is f of t, as a function of the current and prior samples of g, which is the input, as well as the prior samples of f, which is the output. So in other words, what that means is that the function is actually using the history of inputs values as well as the history of its own output values to calculate the new outputs. And so you might say, wait a second, I mean, why, why not just keep like a, if you're doing like an integral, why not just keep like a running sum of every output or every input? Yeah, I mean, you can convert this into a form where you would get that. In fact, if you remember from the lecture, I actually showed how you can derive it that way, where you can do polynomial long division and actually come up with a way where you can sort of generate an infinitely long series of, z negative powers of z, where you can bring it back all the way to the beginning. And that's what, in fact, that's what you would have to do if you only wanted to represent the function in terms of the input signal. But the advantage of this approach is that we can use the previously computed output, which is the previous f's, in the time domain transfer function to avoid having to, possibly have to keep track of a running sum of all the inputs from the beginning of time t0. So if that's not clear, don't worry about it. I'm just kind of pontificating here. In this case, the way I wanted you to answer this was to just basically do some algebra. So the first thing that you want to do is you need to get rid of the positive positive exponents of z. So you can have z is fine. Z of 0 is fine, but you don't want anything that is a positive exponent of z. Now you might say, wait a second, that's exactly the opposite of what you said before when you said how to form an S-domain transfer function in a proper way. You shouldn't have any negative powers of s. Now you're saying that you only want 0 or negative values of z. Yes, yeah, that's because, yeah, I understand that's a contradiction. But in this case, we don't want to have positive. I mean, the transfer function, yeah, the transfer function is a ratio of two polynomials, no negative powers of z. But when we do this problem, we want to push all the powers of z into essentially the current time or the past. So basically, what I'm saying is that the exponent of z is representing the time of the sample time, sorry, no, I shouldn't say the sample time, sorry, scratch that. The power of z represents the sample relative to the current sample, the sample number, right? So basically what that means is that what z represents is a sample number, right? So we don't have access to future samples, right? We only have access to the current sample and the previous samples. We have access to the current information in the history. And so as a result, we want to get all these exponents of z into the past. So I'm going to multiply this by z to the minus second power divided by z to the minus second power, which is just equivalent to multiplying by 1. But it gets all these z exponents down to be less than or equal to 0. So I end up with 1 plus 3z to the negative first power divided by 1 plus 3z to the negative first power plus 2z to the negative second power. Okay, and then now what? Well, now I've got to get, basically I got to get f of z by itself on one side of the equation, and then I got to get all of the g of z's as well as all of the f of z's that have negative powers of that are multiplied against negative powers of z to the other side, which again is a little different than what we did with the S domain. So I took all of the f of z's. Well, I've started out by taking all of the f of z stuff and getting it on one side. In this case, it just involves basically a cross multiply. So I took the denominator here and multiplied it against f of z, and the numerator and multiplied it against g of z. So I end up with this. And then I guess I didn't do anything here. I don't know why I have that. That's redundant. Okay, so then we multiply these guys out. So distribute f of z and g of z. So we end up with f of z plus 3 times f of z times z to the negative first power plus 2 f of z times z to the negative second power. So the significance here is that f of z times z to the negative first power represents the the sample of f in the previous time step, the previous time sample, previous step, previous sample, sorry, yeah, the value of f in the previous sample when we convert it to the time domain. And then likewise on the right-hand side, we have g of z plus 3g of z times z to the negative first power. So I'm going to take all of the f of z's that are multiplied against a negative multiplied against z to a negative exponent and move those to the right-hand side. So I'm trying to isolate f of z. And again, why? Because it's my output, right? So I'm going to isolate that. My goal is to get this alone because I want to calculate the current sample of the output, which is f. And then all of the other terms are on the right. And then, so then when I do the inverse z transform, f of z times z to the negative first power will be f of t minus 1. So that's the f. So f of t minus 1 is whatever f was in the last sample. Likewise, g, same thing. You know, g of z would just be the current value of g, which is the input. Now we have access to the current input value, and we have access to the previous outputs, but you know we have to calculate the current output value. So this way we can generate this signal, right? We can generate this sequence of samples for f of t. And then, so what we end up with is a function that looks at the previous two samples of the output, as well as the current and previous sample of the input. And this is what will generate, it'll generate the signal for us. It'll generate the f signal as a function of the g signal. So both f and g, again, are time series, but we're using, you know, part of the output time series to generate the new output as well as the input time series. So I think this is, I think this is, I don't know, I think this is pretty neat. Especially because ultimately this came from an S domain, which was a differential equation. So we're literally generating a series of samples in the discrete space from a differential equation and doing it through trapezoidal integration and according to a specific time step. I make a mistake again. Okay, it should be 2z to the negative 1 in the numerator of the second step. Oh, yes, thank you. Yep, I did screw that up. Thank you. Yeah, sorry, I did these. Yep. Oh, yeah, you're right, sorry. Yep. So this would be, yeah, how did I mess that up? Okay. Sorry. I did these kind of hastily. The review, I decided at the last minute to put these slides together. And this would be negative second. Yeah, sorry about that. I'll fix that, and I'll post these on Dropbox. Okay. Yeah, so obviously I have to carry that through. Any questions about how to do that? Okay, great. Good. Okay, so let's switch now to, so like I said, the exam on Wednesday will have very similar questions to this. So you can expect very, you know, similar types of questions. The difference will be that it'll be a timed exam. So you'll have 75 minutes to do the exam. So it'll be a little bit more pressure than the quizzes because you'll have less time. But the questions will be very similar. It'll be multiple choice. So same kind of format. And then, so you know, hopefully everyone's pretty clear on this. If you have any questions, send us an email, or you can ask now. And I will, like I said, on Monday, I'll do also a review on the first material, the interfacing material, because there was more stuff there, and it's been longer since we've talked about it. How many questions will be on the exam? I don't know yet. It'll be 75 minutes. I guess it depends on what the questions are and how hard they'll be. I'll try to keep it reasonable. But this is the first time I've taught the course like this, so I can't draw on any past experience. Although in 611 we had some complaints that the exams were a little long, so I'll try to keep it reasonable. You know, I guess you should have 5 minutes per question or so, right? So that would be 15 questions, right? I think is reasonable. Seems reasonable, unless we've got some really challenging ones on there. Okay, so let's switch over to, sorry, let me continue my previous thought. So on Monday, I will also I'll review the interfacing stuff. I'll pretty much just kind of run through the lecture real fast, and if you have any questions along the way, let me know and I'll stop and explain. Okay, so let's run over to the next topic. Stop sharing that and go to here, real-time scheduling. Okay, so I'm not sure how many of you have taken 311 operating systems, but even if you haven't, you probably know that one of the jobs of the operating system is to schedule the CPU cores. Well, the operating system in general manages all of the system resources, including memory and the CPU cores. So yeah, the real-time scheduling material. Yeah, good question. So real-time scheduling, I don't think I'm going to put this on the exam. I was going to wait and see how I did time-wise, but based on where I'm at right now, I don't think I'm going to have enough time to get through this whole lecture, especially if I do a review on Monday. So I'm just going to introduce this real-time scheduling stuff. We'll finish it after the exam. It's fairly short, but the exam, just to clarify, the exam will only cover control theory and interfacing. It won't include this new material. Mostly because I don't have time to give you a quiz on the real-time scheduling because of Monday. We had off on Monday, so I screwed up. I forgot that we had Monday off, so as a result, we got pushed behind. So I'm going to push this real-time scheduling material off. When can we expect the next lab? I don't know. I'm relying on the. I need to discuss that with the TAs. The TAs are the ones that do most of the work when it comes to planning the labs, mostly because they're the ones that grade them. It used to be in the past, I used to plan the labs out. I would design the labs, and but the TAs would then have to grade them, and I didn't give any consideration to grading, and it worked out better to have them do both. So we'll let you know hopefully within the next couple weeks. Okay, so real-time scheduling. So the operating system manages system resources, including the CPU cores, but this is about scheduling in particular. So what does scheduling mean? It means that the operating system will assign each of the tasks that are currently executing to specific time intervals on the CPU or on all the CPUs, if you have multiple CPUs, as most machines have these days, although not necessarily cyber-physical system CPUs. And depending on how the operating system chooses to do that and how it arranges the time intervals that each task gets to run on the CPU for, each task will complete at certain times. But a traditional operating system doesn't have any constraints as to when each task needs to complete. And generally speaking, operating systems make a good faith attempt to be fair, at least among tasks having the same priorities. Although, in general, when it comes to user tasks, they usually have the same priority. You can change the nice level, you can change the priority, but generally speaking, tasks have the same priority, and you just want to be fair. You don't want any task to starve another task, but there's no guarantees on when they'll finish, right? That's the problem. But what if a task or a set of tasks, what if they need to complete by a certain time, which is in real-time scheduling is referred to as a deadline. And also, like, what if the operating system has a set of tasks and their associated deadlines, but what if it's impossible to meet those deadlines, given that, you know, the task set and their deadlines and the CPU resources that are available? It may be impossible. But if it is impossible, how does the operating system know if it's, yeah, that's a good point. Thank you. Yeah, exactly. It's kind of like you when you're in school. You know, if you take too many hard classes with projects, and you have more projects that are due than you physically have time to finish. But, you know, as you know, when you register for classes, you don't know if that's going to be the case. You generally don't know until you start missing deadlines, which is why we do advising. Basically, the advisor is supposed to predict that for you, but it's a very imprecise art. Real-time scheduling is designed to be precise, to be able to give guarantees that you can meet your deadlines. So there's really two questions. Number one is, what is the algorithm to use to do the scheduling, the actual scheduling? So you have a set of tasks. How do you decide how to schedule them so they meet their deadlines, assuming it's possible to meet their deadlines? And second, how do we know if you can meet the deadlines? What sort of way can we tell if the demands are feasible? So it turns out this is a really hard problem. And when I was a grad student, I used to think that this was going to be solved at some point, like, you know, we'd figure this out. But it turns out that, as far as I know, there aren't any open source or free real-time operating systems. They don't exist. There are real-time operating systems, but they're all commercial and they are very expensive. They're all proprietary. It's really, this is a hard problem, and it's something that hasn't been sort of solved to the point where the solutions are free or public. It's all like kind of black magic, kind of. It's tough. And to this day, there's no real-time, like, you can't go and download a real-time operating system for free. You know, it's kind of a very sort of specialized market. But yet, they're used a lot, because it turns out, you know, you might be wondering, well, how does any of this apply to cyber physical systems? That's the topic of the course, right? Why are we talking about operating systems? Because as we just got done talking about, if you have a control algorithm, a controller, the controller operates in the discrete time, discrete time, and when you design the controller, you design it to be stable, and it has to be, when you do the Tustin transform, you have a t term, you have a time step, that time sample time. And when you set that value of t, when you do the Tustin transform and design your controller, you have to hold the CPU accountable, or not just the CPU, but the whole control system has to be accountable for meeting that time step, meeting that sample time. It has to be able to send a signal to the controller by that time step, or else the controller may not be stable, or the whole system may not be stable. So think of it like a cruise control in a car, right? There's a computer that controls the cruise control, and it has to apply adjustments to the acceleration in order to maintain a certain speed. The system is obviously stable. Normally, you expect it to be stable because it's supposed to hold at a certain speed. If the system were unstable, the car would just accelerate, you know, uncontrollably. In an unbounded way, and it would do that if you didn't design the controller right, but it would also do that if you missed the deadlines and didn't achieve the t, because if you don't hit the right t value, then your Tustin transform is now no longer valid, and so any guarantees you made about stability when you design the control would no longer be apply, right? So basically what this all means is that real-time scheduling is critical for all control systems, basically. Now, if you are only running one control task on your CPU, it's not really that big of a deal. But as you might imagine, what if you have a CPU that's controlling multiple things? An example of this would be in robotics, where you'll have a separate controller for, say, each joint on a robotic arm, but you don't necessarily want to have different processors for each one. You may want to run them all on one processor so they all have access to shared data, to shared input signal. So this is wildly important for real-time scheduling. And also, as I mentioned at the beginning of the class, cyber-physical systems and embedded, the types of embedded CPUs used for them are usually pretty cheap. They're not powerful CPUs. They run at a low clock rate. They're usually one core. So you have to be careful with those, that they meet their deadlines, especially when they're being time division multiplexed amongst possibly multiple control jobs. So when I say task, I'm talking about a control algorithm that's running possibly with other control algorithms, each of which is a task. Now, of course, when in general, when you talk about tasks on a computer, it's basically any process, any program running. But in this case, I'm talking about these these tasks that are doing something important to control the physical world in some way. So yeah, I basically mentioned this. One of the big problems, though, is the execution time, because computers have a lot of uncertainty when you run a program and you're measuring its execution time. There's uncertainty in the execution time, and that's because computers can be non-deterministic, because you've got different memory access times depending on the cache performance. Your memory access time changes, especially when you're running multiple parallel tasks that may corrupt, or not corrupt, but pollute the cache between the when you context switch. It's very hard to predict the memory access time. But then you've also got interrupts and exceptions that are happening. We talked about that in the interfacing lecture. Interrupts and exceptions are inherently unpredictable. We don't know when they'll happen. Now you might say, well, why not just disable them all if you're doing a controller? Well, you can disable a lot of them, but like, for example, the timer interrupt, you can't. You have to interrupt periodically to potentially know when to give an opportunity to switch the CPU to another task. But you also have data coming in, that sensor data that you may have to service, so you can't predict any of that. You just don't know when it's going to happen, and when it happens, it's going to add overhead. And also there's sometimes there's data dependent behavior, like you get one piece of data from a sensor and you may need more time to process that than another type of data. Now, in the control algorithms we've looked at, that wasn't the case. They were deterministic. They were basically, the equations that we looked at when we did the inverse Z transform. But there are more complex. Some of the more complex controllers, like for example, when you do image processing, you're looking at a camera. You've got your Tesla. It's got cameras on it. The cameras are looking for lane markers and other vehicles and people. And so, depending on the number of features, which are like points of interest, like corners and stuff that are in the frames, it may take more time to process certain frames than others. So there's this data dependent behavior. So the point of all this is that it's very difficult to know how long it takes to run a task. In fact, it's virtually impossible, and that's one of the problems with real-time operating systems and real-time systems. So generally, what you're trying to figure out is the worst-case execution time. So when we talk about execution time in this lecture, I'll be talking about worst-case execution time. But even the worst-case execution time is impossible to figure out, really, because if you look at the execution time, it usually will follow a statistical distribution, like say, for example, I'm showing a Gaussian distribution, a normal distribution, and there isn't really a maximum and minimum for a Gaussian distribution. It sort of just kind of goes to, it sort of extends out infinitely, right? So one way you can approach this problem is you can figure out confidence intervals. So for example, if you take the standard deviation of a normal distribution and you multiply it by 2.326 standard deviations up from the mean, will give you a 99% confidence interval that all of the samples will fall within that range. You know, basically plus or minus 2.326 standard deviations from the mean. So what that means is if you take the mean execution time of all the observed, you do an empirical measurement, which means you measure a bunch of runs. You take the mean, then you can be 99% confident that the worst case execution time is 2.326 standard deviations above the mean, right? And likewise, you can go up to 99.9 or 99.99. Sorry, that's a typo. There should be a decimal point there. So 99.99% confidence would be 3.719 standard deviations. Okay, so that's one way to do it, although there's still a very small chance that you may have an execution time that's longer than that, in which case your real-time schedule may not work. But the problem is that you can be reasonably confident, obviously, if it's 99.99%, that you won't miss a deadline. And also, missing a deadline, you're probably not going to miss it enough to destabilize the controller. But you can never be certain. Another point here, though, that I want to make is that you don't even really know for sure what assuming you're treating the task as as kind of a black box, you don't necessarily know that it's a Gaussian distribution of execution times. You may discover my VPN disconnected. Hopefully you guys can still hear me. Yeah, can you guys still hear me? Uh-oh. Okay, hold on one second, sorry. Can you hear me now? Thank you. I guess, yes, good. Okay, great. Sorry. My VPN disconnected, and I just wanted to make sure that that didn't cause Blackboard to lose its connection. Okay, cool. All right, so where are we at here? So yeah, so anyway, it could be that there's, if you look at the actual internals of your task, there could be, 3 different control paths that all have their own Gaussian distributions. And the cool thing about that is if you can break it down into a mixture of Gaussians and then take the confidence interval, what you may find is that by decomposing it into multiple Gaussians, your standard deviation of each of the individual Gaussians is smaller, and thus if you just take you add the standard deviation to the mean of the one furthest to the right, you'll get a tighter worst case execution bound than trying to take all the data as one big distribution, if that makes sense. So in this case, this is the same data, but I'm assuming it's 3 different distributions. So the worst case execution time, if I measure it as if I base it off of the most expensive of those distributions, is better than if I just modeled the whole thing as one distribution. Okay, so my point there is that it's you want to that's an approach for calculating worst case execution time. Okay, so now let's talk about scheduling. In general, as I mentioned, the task is code, or is a running code, executing code that performs a computation. It generally is something that tasks can come and go. They can be generated in response to a trigger or a timer. Tasks can there's multiple states a task can be in, but the main ones are ready, meaning that it is waiting to be executed, but it isn't being executed. Or it can be asleep, which means it's completed execution, but it's waiting to be run again or dispatched again, or it can be currently executing. So the goal is to find ready tasks and select among ready tasks and switch them to the executing state. If you only have one CPU, then only one task can be in the executing state at a time. If you have multiple CPUs, then you can have one task per CPU executing at one time. Okay, so let's take a look at why real-time scheduling is hard. So let's assume that we have 4 tasks, and each of them has a different execution time, or rather a worst-case execution time. These are in milliseconds is generally the granularity that you're working in with an OS. Oh, and by the way, one of the things I mentioned at the beginning of the semester that cyber physical systems and embedded systems often don't have operating systems. So would this apply to those? Yes. In fact, you can implement these scheduling algorithms in bare metal, or in fact, some real-time operating systems, like, for example, I can tell you that Texas Instruments has one called SysBIOS, which is their proprietary real-time operating system. And in fact, it's not an operating system really as you would think of it. It's more of a library that you use. So you still do bare metal programming on TI's DSP chips, but you can link it, you statically link it with SysBIOS, which they call an operating system, but in reality you just call functions that tell it that set up that you pass it function pointers to your tasks, and then it will then you call a function that says go, and then it will be responsible for scheduling. So it's doing what an operating system does, but without really an operating system. So some real-time operating, quote-unquote, operating systems work that way. They're just like kind of libraries that run on bare metal. So keep that in mind. Okay, so if you have a task, 4 tasks rather, with computation time or execution time or worst case execution time listed, and then you have a deadline. So let's say you have a 40 milliseconds to run task 1 and a 76 millisecond deadline, and then the 3 other ones are shown there. It turns out that with these 4 tasks, if we assume we'll take the approach initially that this is non-preemptive, meaning that once we start running a task, we're not going to interrupt it. We'll let it run to completion. That's the kind of the simplest approach to this. And under that approach, then basically we just need to figure out an order, to run the tasks in. We just have to choose like which order we're gonna run them in, and then every time we run one, we run it to completion. So with 4 tasks, there's 24 possible schedules. Then there's 24 orderings that we can run them in, and so you can look at these. You can view these schedules as a timing diagram, where each task looks like a signal. And if it's basically, it's going to be 1 or 0, that meaning which represents whether it's running or not. Whether it's basically if it's executing or if it's just ready. And then you can put lines. So these are timing diagrams like the ones you looked at before with the protocols. But in this case, the horizontal axis is time. The vertical axis is basically for each task is 0 or 1, and then we can show then a vertical line signifying where the deadlines are for each of these tasks. So I wrote a program that generates these enumerations and generates the timing diagrams for all of them, just to kind of to visualize them. Because I remember when I was taking real-time operating systems, I was often like, when I first heard about it, I was always kind of confused why this was so hard. Like, what's the big deal? Like, I think it's easier if you can visualize it. So in this case, we got the 4 tasks, and we choose to run task 4 first, and then task 3. Now, notice how task 4 runs and finishes well before its deadline. Then task 3 runs next, and it runs after task 4. So, it switches to high when task 4 switches to low, right, on the timing diagram. And it meets its deadline because it, basically meeting deadline means that its falling edge is to the left of the deadline marker. Task 2 then runs, and this is just like, this is just one of the enumerations, right? One of the possible orders. I'm going to go through them all. This is the first one I got. So task 2 runs and it finishes before its deadline, and then task 1 runs. And notice that task 1 misses its deadline, right? Because it doesn't go from 1 to 0 until it gets to the right of its deadline marker. So this is an invalid schedule. Now you look at schedule number 2 is the same as schedule number 1. I think the only difference is that we run task 1 before task 2. So notice in this case we meet the deadlines. All 4 tasks meet their deadlines. Task 4 and 3 meet them because they did the same thing they did in the last schedule. Task 1 runs 3rd instead of 4th, and so it does barely meets its deadline. And then task 2 runs and it barely meets its deadline. So again, the point here is that you can only run one task at a time in this case because we have one CPU, and assuming there's no overhead to switch tasks, which is not the case either. But there's one schedule that works. And then number 3 doesn't work. This one was kind of a disaster because we ran task 4 and then we ran task 2 and then we ran task 3, and this means that task 3 misses its deadline and task 1 misses its deadline. So then we go schedule number 4, 5, and 6. All miss their deadlines. At least one task misses deadline in each of these. So task 3 meets its deadline horribly. In this 4 and 5 task, let's see where we at here. Task 3 horribly misses its deadline again, and then in task 6, task 3 again misses. So I guess it's task 3 missing in all 3 of those cases. So as you can imagine, we go on and on and on, and it turns out that very few of these schedules will meet their deadline, but there are some that will, but they're rare. They're hard to find, and so we need a way to find them. So I'll go ahead and just end it there today. And on Monday we'll come back, and like I said, I'll do a review of the interfacing material. If you have any questions, that would be a good time to ask. And then I might continue lecturing on real-time scheduling, and then Wednesday we'll have the exam. Okay, any questions? Okay, good. That sounds good. All right, then have a good weekend, and we'll see you on Monday. And there's no quiz, at least at the moment. If I post a quiz on this, I'll let you know, but I don't expect to. And we don't have any programming projects available. Yes, good question. The exam will be during. Well, actually, wait a second, Robert. Now I'm thinking. I think in 611 we had you could take the exam at any time on exam day, but it would be better to have it during class time. And the problem is, though, that if you didn't register for section 2, then anyone in section 1 could potentially have another class during this class time, right? So no, I can't make it during class time. That wouldn't work. It has to be, yeah. So it will not be during class time. Sorry. So we'll have it. You'll take the exam. You'll have a time limit, but you can take it any time on Wednesday. Okay, on next Wednesday. Okay, so it won't be during just class time because we may have conflicts if we do that. Okay. There's no, well, the quizzes were designed to be the kind of the practice exam. If I had taught this course before, Yeah, any time Wednesday, so it'll be midnight to midnight is the way I did it in 611. And no, we won't have class that day. No, no class. I don't want to do that because if this was a traditional class, we wouldn't be able to have class and in the exam on the same day. So I mean, I want to try to be. I don't want to exploit the virtual version of the class to try to you know give you more workload than you would have in a normal class where we'd have to be in the room together. So no, there won't be any class that day. Also, it saves me from having to. It saves me too from having to prepare for it. Okay, thanks, guys. I'll see you on Monday. Thank you.